So today's talk will be more of a seminar style talk, and I will review some of the things that we discussed in the last 3 times.
You think the earlier talks were very elementary.
Okay, so to remind you, we want to look at 6-dimensional theories with which preserve at least 1,0 supersymmetry, and we want to look at the focus of my talk will be on non-gravitational theories, which are UV complete. And there are 2 classes of such theories which are known: the superconformal field theories and little string theories. And we want to look at their F theory, how to realize such theories in F theory. So we are going to compactify F theory on a Calabi-Yau threefold, which is elliptically fibered, and this is known to preserve 1,0 supersymmetry. And as I discussed, the such elliptic fibrations are described by a Weierstrass equation. Let me start with the again.
So when you're talking about UV completion, you don't mean UV completion in the sense of the F theory?
No, I mean a 6-dimensional UV completion.
As a field theory itself?
Yes, as a field theory itself. Okay, and here f and g are functions on the base, and we know that if we want to look at this where this elliptic fibration develops singularities, so we want to look at the solutions to the discriminant of this equation being 0. So this will be a codimension 1 locus on the base, because f and g are functions on the base. Because we are looking at the base is 2-dimensional, this will be one complex dimensional curves.
Base is 2 complex dimensional.
Yes, everything is complex throughout this talk. Okay. Now, so in general, a curve can be divided into some irreducible components. So this will be some curve which will be, so there's one curve like this, and another one intersecting it at some point, and so on, maybe with different topologies. So this can be a sphere, this can be a torus, and so on. So these are what I will call the irreducible components of the discriminant locus, or simply as curves. Whenever I will say curve, I will mean one of these pieces throughout this talk. And in general, they will have different type of singularities sitting on them. So because delta has to vanish here, in general f and g will vanish up to some order on each of these curves, and the order of vanishing of f, g, and delta characterize the singularity, the type of elliptic singularity here.
And you said this last time, typically around one of these things you get some sort of monodromy in SL2, whatever.
SL2Z, yes.
So just to, so F theory can be thought of as type 2B theory compactified on a torus, and
no, type 2B theory with an extra torus.
I'm sorry, sorry. So 2B theory is F theory on a torus,
yes.
And the coupling constant is variable over the torus, right?
Over the base. So you're compactifying type 2B on some base. So we have an elliptically fibered Calabi-Yau threefold, and there is some base. So this is where you're compactifying 2B on this, and the elliptic fiber is parameterizing the coupling constant and the axiom.
Okay. So if I begin with 2B,
yes.
and then compactify this on a torus,
yes.
and the dilaton is variable over the torus,
yes.
Then I can think of that
as an F theory compactified on X. This by definition.
Yes.
Okay.
The kind of singularities appearing on a particular curve is somehow correlated with the intrinsic data of the base itself, the intersection form and the genus of this curve and so on. Is it correlated to that?
Sometimes, if you want to impose some restrictions, that if you want to have an SCFT, you want your base to have some special properties, and then there might be some talking between the fiber and the base.
Practically speaking, is my singularity structure constrained to be of a particular type, depending on which curve I pick and how it intersects the other curves?
There can be some global things, right? For example, if you choose some sort of behavior on this curve, and if you had a loop, right? You can imagine that you have choice along these 4 curves, but the behavior on this curve is completely fixed, just due to topology. So these sort of things can happen. Right. So in our situation, such singularities, such singular behaviors were first classified by Kodaira, and I reproduced Kodaira's table earlier, and they were further refined by Tate. In the specific case when you are compactifying down to 6 dimensions. So in Tate's classification, there is some extra ingredient. So Kodaira is basically classifying codimension singularities when the base is 1 complex dimensional. So he's just classifying some points, some 8-dimensional theories. So I should also say that physically each of these different singularities correspond to different 7 branes, and there are some gauge fields which live on them. Right. So when you go down to 6 dimensions, you can have this point becomes a curve, and so you can have multiple curves intersecting each other. And on this curve, you can have a monodromy of the elliptic fiber as well, because these curves are making a puncture effectively on this curve. And so there is a classification.
Around the curve, you're saying.
Yeah, as you go around the curve, there can be an extra monodromy of the singular elliptic fiber.
So there's always a monodromy as you go like this.
As you go around, yeah.
But then in addition,
The singular elliptic fiber itself can have a monodromy.
Because of this intersection.
Yeah, because there are these punctures here. And Tate classified all such behaviors. So Kodaira's list is refined into various singularities. Each singularity splits into some type of singularities.
basically you're saying that the monodromy jumps as you go through these touching points, and that jump might not come back to itself if you go around it. I mean, if you look at this monodromy,
Yeah.
this one, as you
Yeah.
go through here, there's a jump,
Mm-hmm.
and then you go through here, there's another jump, and may not come back to itself. That's what you mean by the monodromy.
Yeah. Yeah. Okay. Okay. So right, physically what is going on is that we are wrapping some 7 brane on these curves, and we want to look at what is the reduced theory in six dimension, which occurs at low energies.
And at these intersection points, are there new kinds of brains? Are there 5 brains sitting there somehow?
Sometimes yes, you can have in type 2b. Sometimes they have interpretation as orbifolds. I don't think they have an interpretation as. I have never seen them interpret as orientifolds. Okay. Right. So in general, our problem is the following: we have these 8-dimensional gauge theories living on each 7 brane. We are compactifying them on some curves, and we want to see what is the low energy theory in 6 dimensions. So last time we were studying compactifications in the presence when there were no O7 plus planes around.
Sorry. Okay, elementary questions, but these curves, they have to be abstract. Their shape is fixed. They have to be holomorphic curves or something like that. I mean, sorry, I don't know, whatever. Like you can't draw them wherever you want, right? You want to preserve supersymmetry.
Yeah, they are defined by some complex equations, some holomorphic equations.
And that's all? That's the only constraint?
Yeah. Yeah.
So, but then they can move around.
They can move on.
Okay.
So this is like just D7 branes moving around.
Moving around, and whatever that was, even they wiggle around, they still preserve supersymmetry.
Yeah.
Modular space of Calabi-Yau threefold.
Well, sorry?
Calabi-Yau threefold as a whole manifold.
In moduli space. No, I mean on
No,
a given
no.
color.
That space in which it's moving around is the modular space. I mean, typically it's non-empty.
The space in which I thought it was moving around on the Calabi-Yau.
No, so he's talking about moduli space of all Calabi-Yaus.
Yeah, but what?
That's
Not all
param.
I mean, sorry, I'm just saying that there is this structure is not rigid.
This the moduli space of the thing with the 7 brains, you're saying.
In model space, you mean because you usually pick the complex structure and in that there is
Yeah.
constraint in moving these parameters. So you fix the Kähler structure and the complex structure and still it's like shifting 7 brains parallel to each other.
It's moving the
It
7
does not change anything.
That's what I
I
think.
mean, in the interpretation of a Calabi-Yau, there are no 7 brains anymore. You can just think of everything in terms of geometry.
Now this is, I don't even know how this is related to a Calabi.
From type 2 point of view, this would be a 7 brain, but from F theory, on a Calabi-Yau point of view, it's just a Calabi-Yau.
Ah, I see.
So that's geometry.
Thank you, thank you.
Right. So the general philosophy of F theory is that you can geometrize all of physics.
Okay, but then this makes it sound like there's a small moduli space, a finite dimensional number of parameters. Why from this that's because it's compact space.
Yeah.
Yeah. Okay.
Okay. So last time we were considering compactifications of this type, in which there were no O7 plus planes around. And in this case, there is a sort of correspondence between the 8-dimensional gauge theory living on the 7 branes and the final 6-dimensional theory that you obtain at low energies. So let me describe what this correspondence is. So what I'm saying is that you can go to a point in the moduli space of this compactification where this some nice properties hold true, which I assumed throughout the last talk. So to each curve, you have either you have a simple factor of gauge algebra of 6D gauge algebra, or nothing. So
Nothing is when you don't have singularity.
right, when you don't have singularity. Well, I mean, yeah.
I thought all those curves had a singularity. So I misunderstood. I thought each of those curves that you draw
Yes.
necessarily have a singularity.
No, I'm drawing curves in the second homology.
Oh, I see.
So some of them contain singularity, some of them don't.
I see.
The curves are in the base, right? Depends how you choose
Yeah.
your pattern.
Okay. And if you have a simple factor of 6-dimensional gauge algebra, then it necessarily lives on a single curve. So this is sort of the statement that there's a point in the moduli space where the Kaluza line reduction from 8 dimension to 6 dimension is almost trivial, up to this thing pointed out by Tate, that there can be some monodromy, so the 6-dimensional gauge group need not be the 8-dimensional gauge group, but some subgroup there is of it. Okay. And we saw that this correspondence was crucial for the anomaly cancellation. I wrote down anomaly cancellation in terms of the intersection number of the curves on one side of the equation, and on the other side there was some purely gauge theoretic data which corresponded to that simple curve.
Right, yeah, I guess my first question relates to that. So that's some anomaly condition which relates the intersection form of the base to the possible fibrations that you can have, right? But is it also a geometric condition? Is it a condition that is necessary to have a Calabi-Yau, or it's actually purely physics condition that the anomalies should be?
It has not been fully explored, but in all the examples in which you explore this question, it turns out that it's a geometric thing.
Or
You
so
can
it's
derive
a
it from
necessary
geometry.
condition for this being a Calabi-Yau.
For right, so to have the global structure of a Calabi-Yau. Right. I mean, basically, you're studying these functions f, g, and delta on this base. Right, and because they're holomorphic, I mean, they need to satisfy some conditions as you go from one curve to the other curve. how did, yeah. Okay, right, so what were these conditions? Let me write them down again. So we had some, I'm parameterizing my curves by a label A. And A also parameterizes the simple factors in the 6-dimensional gauge algebra. So here I compute something from the purely gauge theory side. This rho A's are the dimensions of the are the representations of the in which the hypermultiplets transform. If I look at the gauge algebra GA, so it's the representations of the hypermultiplets under the simple gauge algebra GA. And here there's some purely geometric data. K is the canonical divisor on the base, which is dual, right? And dAs are the curves themselves. And there were some similar conditions.
But these were the anomaly cancellation? The
Yes.
anomaly conditions?
Yes.
So you mentioned this before, but the matter is, just to remind me, again, the matter is coming from these intersection points? Is that right?
Yes. So mostly, sometimes it can also live on the curve. If you have adjoint matter, you can Higgs it to get antisymmetric and symmetric matter, which can arise in SCFT and which lives on these curves.
And there's an algorithm for what kind of intersection gives you what kind of matter.
Right.
And it's usually bifundamental. It's usually like bifundamental, or just all kinds.
Right. So we deduce it from anomaly. In the approach of these people, they deduce it from anomaly cancellation. What should be the correct matter?
And there's no more physics way of trying to understand what. There's no more dynamical way of trying to understand the matter.
For some kinds of matter there is,
Okay.
but as the matter gets more complicated, you have less and less tools, geometric tools to understand it.
This is what kind of anomaly is this?
Gauge anomaly and mixed gauge gravitational anomaly. So this one is coming from mixed gauge gravitational anomaly, and I'm writing down anomaly polynomials. So there was supposed to be a trace R squared multiplying this.
But once you fix these gauge groups, the matter charge under them just is fixed, or there are choices.
If you fix the geometry, then you should get a unique theory.
No, from let's say bottom-up point of view,
Yes.
you have two gauge groups, and now you want to think of all sort of bifundamental or
Yes.
some.
Then it's not fixed. You have choices,
You have choices.
but they will be
From
realized.
this point of view, it seems that you don't have choices because the gauge group would be realized by these two curves
Mhm.
with some particular similarity on them, and then they intersect in some particular way. Now, what can I change to change the matter?
Mm.
Change perhaps the intersection number or something?
Sorry. No, sorry. Mostly. So you can replace one of, right. So suppose you're looking at this gauge algebra, then there will be matter coming from here and from here. You can
I mean, charge under two things.
charge under two things that should be fixed. Yeah. Yes. Yeah.
So your question is, are there more six-dimensional gauge series than what comes from this construction?
Yeah.
And the answer is no. It's
No, that's
all of that comes only from this kind of construction. Yeah.
Also, he was saying that he doesn't really know what the matter is at the intersection. That his only way of figuring it out was this anomaly.
Yes. So
But the question is, there are multiple solutions.
Whether there are multiple solutions, right? But I mean, he wouldn't even know if all of that, because, right, if there were multiple solutions, you wouldn't know which one,
What to change?
what to change, yeah. Maybe you could put some,
no, but so matter has to be very fixed, right? So suppose you choose bifundamentals over here, then you still need some extra matter charge under this group and these groups separately. So the geometry of the base is different.
All these equations together, which is a global set of equations,
Yes.
and then figure out solutions to those equations, write down the matter.
Mm-hmm.
And now look at the matter charged into two gauge nodes. Are there multiple solutions or a single one? If there are multiple solutions, then how to access all of those using geometry?
or can they all be outside?
I think then it will be unique. Yeah.
Well, there are never multiple solutions.
Yeah. That's what allows the classification to take place.
So given the gauge group structure,
Mm-hmm.
you could just use field theory to classify the matter, right? Because there's just a field theory. What this whole thing is giving you is some insight on the gauge group structure.
Mm-hmm.
Is this right?
And there's some non-Lagrangian matter which does not come from a gauge theory.
Okay. Yeah.
I mean, provided you specify what the representation content of the matter is or not.
No, he's saying that is just totally fixed by cancelling all anomalies. You give the gauge group structure, then and require all anomalies to be cancelled, then there's always a unique solution to what matter.
Yes. So the main condition is coming from the fact that look at this equation. In general, this will contribute something like trace fa squared and a trace fa to the 4 term. So in general, you will have something like trace fa to the 4, which must vanish in such an F theory setup, because F theory is going to give you only trace fa squared term. So the vanishing of this fixes what kind. If you start giving, you cannot give multiple kinds of matter. There's only a discrete number of choices you can give.
Then I would ask, how come you, who gave you these anomaly equations in an absolutely general setup in the context of six-dimensional theory? How do you know that?
So
what gave,
the
what
general
gives you-
story from the point of view, from the bottom point of view, was that you look at this anomaly, it decomposes into two parts. You require that this vanishes, and then you're left to deal with this part. If this part is positive definite, then you can cancel it by coupling tensor multipliers to your gauge theory.
The great ones.
Yes, okay.
So it's a purely field theory analysis. Those kind of anomaly polynomials that can be cancelled by the Green-Schwarz mechanism, the only kinds allowed.
And here F theory is giving you a very particular Green-Schwarz counter term. Okay, so today I want to describe compactifications in the presence of O7 plus. And we will see that both of these properties are violated in the presence of O7 plus. So what if you focus on a single curve, you will find that in general you will have you will have some semi-simple factor of gauge group. And if you look at a simple factor of gauge algebra, in general it will live over multiple curves. So it will be shared by many curves. And there will be no point in the moduli space of compactifications where you can restore these two properties. So analyzing F theory setups will become more complicated, and the classification will be much more tedious.
This will not belong to Codera's classification. O7 plus.
No, O7 plus is something physical. It's,
Right.
Okay.
There we had an O7 minus
Right.
as one of the choices.
yeah, so I will discuss O7 plus and its relation to elliptic singularities.
By the way, so when we talk about these statements like this, simple factor corresponds to single curve and so on, of course this is a vector space of curves, right? We can take take a different basis of the second homology, and that would give you a different set of curves. Now, I mean, if there is a vector space structure, then what does this single curve mean?
No, but it's coming from this irreducible component of a discriminant locus, right?
No, so from the base point of view,
Yes.
let's not talk even about the elliptic fiber. From
You
the
look
base
at the
point-
discriminant where it vanishes, and you look at the irreducible components of it. That will almost completely fix the curves I'm talking about. Only the ones which don't contain a singularity will have some choice.
And they don't have gauge groups anyway.
They don't have gauge groups anyway. Okay. Okay.
When you say that a simple factor may come from multiple curves, it would mean even from the curves which does not have that singularity.
Which at least have that sub singularity. So the singularity must be higher than the gauge group that you're talking about. It must contain the gauge group. And it will turn out that most of the other group is broken away or goes into some other group. So I'm just saying that the Kaluza-Klein reduction from 8 dimension to 6 dimension won't be trivial.
In the presence of these
O7 plus. Okay, so in this talk we will have 3 goals. So first is to understand why this correspondence is violated when you include O7 plus from the point of view of type 2b.
So roughly there will be Wilson lines or things like that.
Right, right. And some fluxes of
Right.
RR2 forms. Okay, and to understand how these anomaly cancellation equations are modified when this correspondence is violated, because this relied on the correspondence. And then to see that you can construct new 6-dimensional SCFTs which were not included in the previous classification if you include O7 plus.
So it'll give you new gauge group structures that you couldn't have got otherwise. Is that true?
New theories.
New theories, but I want
Yeah.
to understand in what ways they differ.
So for instance, SO-SU by fundamental matter, or SU with symmetric matter.
These were present in the classification from the field theory.
Yes, they were present in field theory. Okay, so let me start with the first aim to understand why this correspondence is broken in the presence of O7 plus.
And I'm sorry to keep interrupting, but let's say that you could have got SOSU without this. Then you said that the matter would be completely fixed. Just by anomalies, right?
Yeah, so I will show you that SO-SU bifundamental could not appear in the previous classification.
Which must mean that SOSU could not appear.
SO could appear and SU could
But
appear.
SO and SU together.
Together, yeah, no sort of matter could appear in between them. Right, okay. So to demonstrate how O7 plus forces violation of these 2 conditions, let me look at some simple models which can be realized in type 2A. So let's start with putting some D6 branes along 0, 1 along these directions. So let's say I have n D6s. This direction is x6 and the other direction on the board is x9, say. Then let me put ns5 on this, which are completely submerged inside D6. So let me put 2 ns5s. And now let me compactify this x9 direction and take a T duality along that direction. Then you obtain a type 2B setup in which, so in general, if you compactify a direction transfers to ns5 and take T duality, you obtain a top-notch singularity. So you obtain a circle fibration such that the circle shrinks at the location of ns5, and then the D6s will just become D7 branes. So you will have D7 branes. So the middle one will become D7 branes wrapped on a sphere. So the circle will shrink at these 2 points, and the other 2 infinite segments will become cigars wrapping D7 branes. So you'll get a geometry like this. So in the F theory language, you have Kodaira type IN singularities on all of them. This just tells you that you have n D7 branes on each of these things. And we can read what is the low dimensional gauge algebra, what is the low dimensional theory from type 2A side. So you have an SUN attached to this curve, an SUN attached to this one, and an SU1 attached to this one with bifundamental matrix in between. So in this situation, you see that the correspondence is clearly holds. To each curve, you have a simple factor of gauge algebra, or of the 6D algebra in general, and to each every simple factor of the algebra is associated to a single curve.
And this is the example you started your first lecture.
Yes.
This one you had.
So, and then we have bifundamental matrices, that's what you said.
Okay, let me keep these conditions here because I'm going to modify them. Okay. Now let me slightly deform this example. So let me separate this stack of D6 branes along the X9 direction into two stacks. And I also separate the NS5s in the following fashion. So again, I have X9 here and X6 in this direction. Say you have M D6s here and N D6s here. Okay. So now let's compactify X9 again, take T duality. What will happen is that you obtain exactly the same geometry. This time you have Im plus n living on each of them. With some holonomies on these, on each of these curves for the gauge fields. But from the F theory point of view, where you just care about the geometry, this is exactly the same geometry as this. And now if you look at the 6-dimensional algebra, you can read it from the type 2A setup. You find that on this curve you have an SUM and an SUN. On each of these curves you have an SUM and an SUN. Such that these two SUMs are identified together and these two SUNs are identified together. And there is some matter in between these two and these two groups.
So in order to go from here to here, I should think of the crosses first becoming lines and the lines joining up above and below. Is that?
So you compactify the X9's direction on a circle,
Yeah.
the above direction, and this circle pinches off at the location of NS5s, wherever the NS5s are on this X6 direction. So here is X6 and X9 again.
Yeah. I see.
So that sphere will be oriented like that, along the line connecting the two
Yeah, from in between these two NS5s. So this sphere lives in between these two pinches.
So compared to this, so here it's on the line connecting the two NS5s, which is along the D6s.
Yes.
But there it will be in that.
Yeah, it doesn't matter, right? So this thing will dualize to a flux for the NS-NS2 form in type 2B. So you have some fluxes here. Okay. Right. So now you see that both of the points in the correspondence are clearly violated. So why didn't the people in the past, so I did not include O7 plus, right? Why didn't people in the past consider these sort of situations in F theory? The reason is simply this, that there is you can tune this setup to go to this setup. So there is a point in the moduli space of compactifications where the correspondence holds true. In general, you can argue from the F theory M theory duality by compactifying F theory on a circle, on a Calabi-Yau times circle, it becomes M theory on that same Calabi-Yau, and you can argue that all of the data becomes physical data of the elliptic fibration. All of the data of elliptic fibration in F theory becomes physical in M theory, and then you can show that there exists a point in moduli space where this correspondence holds true. Now the claim is that in the presence of O7 plus, the correspondence will be violated because the duality is modified between M theory and F theory. So let me continue with type 2a and show you what will happen if I try to include O7 plus. Hmm?
Is the Higgs branch of the system?
This is, yeah, it's a part of Higgs branch. Yeah.
You have moved simultaneously on tensor and Higgs branch.
No, I did not move on tensor branch. That was corresponded to the motion of relative distance of NS5s.
But that is separated, right? NS5s are separated.
No, in this direction. 1, 0 tensor branch at least.
Yeah.
This is a 1, 0 setup. So the tensor branch was just this x6 direction, one real direction.
Right.
Yes.
And now you have also moved on to the Higgs branch.
Yes,
He's
ah,
not moved
okay.
on the tensor branch at all because he's separated only like that.
Yeah, so I was on the tensor branch here already, and then I went to the Higgs branch too. Yeah. Okay. So now let me consider.
Usually these things are kind of bounded by supersymmetry, right? You either move in this branch or that branch. And the Coulomb branch is equals to 2 or Higgs branch is equals to
Yeah, but there is an intersection here.
Okay.
Okay, so now let me consider type 2b with orientifold planes, O6 planes. So I have again some d6s and an O6. Then I have a half NS5 brane. So on the orientifold locus, a full NS5 can break into 2 half NS5s. And whenever you see a half across, it's a half NS5 in my pictures. Okay, right. So if I start, let me start with some d6s and a particular chirality for O6. Then across a half NS5, the chirality of O6 is known to jump. And the number of d6s, again by the cancellation of RR charge at the location, because O6 minus and O6 plus have different RR charges, the number of d6s are different. So in this case, you have n minus 4 d6s on the other side. Right, and since I want to compactify x9, I must have another, I must put it on an interval. So I have another O6 planes. So let's say I have m d6s and an O6 minus, and then
We discussed this in the first talk, but can you remind me the link between tensor and the hypermultiplers?
so something like B wedge, not hypermultiplets, just to vector multiplets.
You're trying to see why it's possible to have because there's no coupling.
Okay. So let's take a T-duality of this setup along x9 direction. Then we again obtain a similar geometry. This time, so here on the left side, you are going to obtain, so d6s will become d7s, and O6 minus will T-dualize to O7 minus. So this is the I star singularity, O7 minus with a stack of d7s on it. In the middle, you have a O6 minus and an O6 plus, which T-dualizes to a shift orientifold. And the shift orientifold is what Tate classified. So in Tate's language, this will be known as a IN singularity. So I something something, but a non-split one, which denotes the fact that there is a monodromy around it.
Is there I star n plus n minus 4?
I mean, this is just some convention. If you match the I star, the usual I star naming with.
Probably the label didn't have a minus 4.
There was a minus 4, yes.
But it corresponds to n plus n d7s with an O7 minus.
Yes. Okay, and here let me denote it by question marks because this is some O7 plus thing. Okay. Now we read again from the 6-dimensional picture what is the algebra. Here you will have SO2M on both of these curves. Right. Here you will have USP 2n minus 8.
Sorry, I thought you don't know that, right? That's the question mark.
Question mark is about what is the singularity in F theory. I told you the answer, but let me keep it there. Okay, and again you have USP 2m minus 8 here, and then SO2n here. Okay, and these two are joined together, are supposed to be the same group, and these are the same group, and there is some half hypers in the bifundamental. So half NS5s give you half hypers in the bifundamental representation. Okay. So now, can we tune this configuration back to a situation where the correspondence is restored? First of all, you want to put this NS5 back onto this, right? Which is not possible because half NS5 cannot leave the orientifold locus. And again, the second thing is that you can move all of these D6s back here, but then there is an m minus 4. So you must leave at least 4 D6s over here. So there are two obstructions to going to that point. One has to do with the Wilson lines, and one has to do with the flux of the NS-NS2 form. And if you play with more models, so now you will think, right, there is still a very nice point in the moduli space. You just take m minus 4 D6s onto this side, and then you will be left with an SO8. So you just have to keep track of an SO8 around. But it turns out that if you try to include more half NS5s, maybe with some D8 branes crossing them, as you complicate the model, the notion of a canonical 0 on this moduli space becomes less and less, it becomes more and more fuzzy. And you have to just give up the notion of a canonical 0 on the moduli space. So moduli space becomes an affine space without any origin on it. And you have to treat every point on the moduli space equally importantly. So that's what the philosophy I will take. So I will assume that when you have O7 plus, the correspondence is broken, and we are sitting on a generic point on the moduli space. I want to describe every point on the moduli space, how anomaly cancellation works on every point. Okay. So now, before proceeding to the anomaly cancellation analysis, let me review some things about O7 plus. What is the singularity?
So what do we not know at this point? Do we know all the matter on across the?
Yeah, we know everything from type 2A.
Yeah.
But you cannot geometrize everything. So you do not know what it means in F theory to have an O7 plus. Right, so.
And the matter is just by fundamentals?
Yes, half by fundamentals. Okay, so RR charge of O7 plus is equal to RR charge of O7 minus. So the RR charge is what governs the monodromy. So it's equal to RR charge of an O7 minus with 8 D7s, and both of them induce a Z2 Orbi folding action on the geometry. So in F theory, you do not look at the starting space in the type 2B. You look at the resulting space, the physical space after the Z2 action. So from that point of view, when you just look at the resulting space, both of these look exactly the same, an O7 plus and an O7 minus plus 8 D7s as far as geometry is concerned. Okay, so this means that the Weierstrass equation governing both of these will be exactly the same, and the singularity in the Kodaira's list is I4 star. So now, since we were using I4 star for this, let me keep I4 star here, and let me denote this I4 star singularity by a hat. So there is still a crucial difference between these two geometrically. So on this side, you can take the D7s away from this locus and completely resolve the singularity. On this side, there is no such notion. So you are forced to have a singularity. It's a frozen singularity. Now you can stack some D7s on both the sides to make ik plus 4 star and another version of ik plus 4 star with a hat, with the property that this has the property that you cannot completely resolve it. It's partially frozen. Right, so from the point of view of F theory, it's not known how do you distinguish between these two cases. You know that on this you should get an SP group, and on this you should get an SO group.
Sorry, are the tensor multiplets affected by the orient folding?
Which tensor multiplet?
The one that correspond to the.
So it's just there, right? It's just there.
It's just there, and unaffected by the orient.
Yeah. It's just that suppose you had D6s, right, with an NS5, and you put an O plane here, then this can split into two now. So there is an extra tensor multiplet which comes with the introduction of an orientifold. Okay, and in a recent work, Yuji Tachikawa argued that these are the only frozen singularities in F theory, partially frozen singularities in F theory. So these are the only things which have been missing from the traditional literature, and we want to understand them. So this was argued on the basis of M theory F theory duality.
So I missed what ik plus 4 is.
You just stack KD7s more on it. So the fact that these are the only partially frozen singularities in F theory was argued by using MF duality.
Sorry, so you stack what D7s on this?
Yes,
But why not move the D7s away?
you can, but it's still partially frozen. You can only move
But
K
then
number of
reduce
them.
it to a simpler partially frozen.
Yeah, you can reduce it to I4 star hat, but
Yes.
not further.
Fine.
Okay. Right. So the fact that these are the only partially frozen singularities in F theory follows from using MF duality, and in M theory you want to the codimension 4 singularities are supposed to be completely classified. So you just map what those M theory singularities become in F theory, and these are the only ones that you find which are missing from the literature. Okay. Now let me move on to anomaly cancellation. And I will just modify the traditional argument that I presented to you in a talk earlier. So let me set up some notation. Let me use the index A for the curves. So I have curves dA. And let me call the simple factors in 6-dimensional gauge algebra by some index I. So these are the 60 gauge algebras. And right, so let me call them HIs. So these come attached with some 8-dimensional gauge algebra GA. This is the algebra living on the 7 brane, and we want to figure out what is this set of HIs. We are given some, let's say we are given some set of HIs in the resulting 6-dimensional theory. So these are 60 algebras. And this is 8D. Okay, let me use, so in general these HIs are shared over some DAs. So let me introduce some NIA, which is 0 if
What is the DA, please?
D is a curve. So let me introduce this notation of NIA, which is 0 if HI does not live over DA, is not shared with DA, and it is 1 otherwise if HI lives over DA. So we saw that when there are no O7 plus, so in this argument we were going to use two types of coupling in the type 2 theory. One of them was the coupling of 7 branes to the gravity theory in the bulk, and the other was the coupling of 7 branes to I mean the coupling of the B4 of the chiral 4 form in type 2b to the gauge theory living on the 7 branes. So let me first start with the gravity coupling. So when there were no O7 plus, we saw that the coupling takes the following form. B4 is the chiral 4 form in type 2b, RR4 form. Here dA is the curve on which my 7 branes are situated, and delta is just a delta function situated on this. This is an integral over 10-dimensional space-time. NA is the order of vanishing of delta on dA. So for D7 branes, this is just 1. So for D7 branes, it just counts the number of D7 branes. So we see that for D7, the coupling gives us a -1/24. For O7 minus, they are just 2 D7s non-perturbatively. So they give -2/224. And now we know that for O7 plus, the sign of this coupling is just the opposite of that of for O7 minus. So for O7 plus, you have +2/24. So this was a formula which was supposed to hold true when there were no O7 plus. And and now I will tell you how to modify it when you include O7 plus. Right. So let's calculate.
Why is the number of D7s equal to 1? It's so obvious.
No, I'm saying if you have a single D7 brane,
If you have,
that contributes -1/24. So an O7 minus contributes -2/24, and O7 plus should contribute just the opposite sign to that of O7 minus, so it contributes +2/24, because the plus and minus chirality is just talking to the gauge theory living on the 7 branes. They do not care about how they couple to gravity, except up to a sign. So I'm just deducing the contributions of various type 2b branes to this factor, and these are the contributions. So now let's see what does an I star k singularity contribute. So an I star k in F theory corresponds to how much k NO7 minus along with k plus 4 D7s. Right, so and this turns out to be minus k plus 6/24. And k plus 6 is precisely the order of vanishing of delta for I star k singularity. So this formula holds true. Now we know that we also have another frozen version of I star k singularity, which geometrically is exactly the same, but physically has a different interpretation.
I'm really sorry, I'm going to confuse something a little bit. You're computing the D3 brane, the effective D3 brane charge of this. That B4 is what couples to D3 branes?
Yes.
So you're computing the effective D3 brane charge of this configuration?
Yes.
And on what we're on some 6-dimensional compact. We're in it's string theory here,
Yeah, it's 10-dimensional space-time.
and we've got some 6-dimensional compactification,
Yes.
and the remaining 4 dimensions just answer.
Mhm.
Okay, thank you. I thought in the previous setup you were in a 4-dimensional compactification of string theory.
Yes.
Why are we now in a 6-dimensional?
Sorry, we are still, I'm just saying that you have some 7 branes somewhere in the 10-dimensional space-time, which is located at this ds.
Yes.
And the integral is over the whole 10-dimensional space-time.
Right.
So I should say, yeah, some x10.
So then if we were just in a 4-dimensional compactification,
Yes.
then one of those R factors would be sort of trivial.
Then you will decompose B force into into some 2 forms.
Okay.
So I'm not doing the compactification yet.
Okay.
Okay, so let's see what this frozen I star k singularity contributes. So we would expect from this formula that it would contribute the same thing, minus k plus 6 over 24. But physically we know that this corresponds to an O7 plus with k minus 4 d7s on top rather than k plus 4. And so if you just if you just calculate, you find that this gives minus k minus 6 over 24 rather than a k plus 6. So when you have O7 plus, you should introduce some correction factor to this geometric formula over here. And so the correct coupling is B4 minus NA minus 12 SA over 24 trace R squared delta 2 dA, where SA is 1 if you have O7 plus on dA and SA is 0 otherwise. So SA is counting where you have frozen singularities. It's some divisor on the base which counts the frozennality of your curves. Okay, so this is the correction to the gravitational coupling. What happens to the gauge coupling?
I'm sorry, Lakshya, I missed your argument for this essay.
Yes.
How did you get that correction? Just half a second.
So we know that there are 2 versions of I star k singularity. This was something geometric. So if you compute for I star k what NA is, this turns out to be this number. Now I star k has a perturbative interpretation as O7 minus plus k plus 4 d7s, which if you calculate using these contributions, you find this number. So it matches the geometric formula, but for the O7 plus it's something different. So you need to correct it. Okay, so now for the gauge coupling, the coupling when there were no O7 plus planes, the coupling took the following form.
So the lesson is the D3 brane charge of the O7 plus is not determined only by its D7 brane charge.
Only by the geometric charge, whatever is the. This does not count the number of d7s.
But these factors were not. Oh, that was not effectively D7. That was something else.
Yeah.
Wait. So how do you get those numbers? Minus 1 by 24, minus 2 by 24, and so on.
So I know that order of vanishing of delta for IN singularities is n d7 is 1 is n. Okay. So here Fa is the field strength valued in the 8-dimensional gauge algebra GA. So this is valued in GA. But we know that the 6-dimensional gauge algebra is not GA, but rather some HIs, which are composed of these GAs.
Now, this is some statement of perturbative string theory. So we could do this by perturbative string calculation.
Yeah.
We could compute just scattering of P4
Yes. Yes.
and check this.
Yes. Yeah, so that's how you know that for O7 plus you should reverse the sign. This came from a perturbative calculation. Okay, so now in our case, what is going on is that we have some holonomies on each of these DAs and some fluxes whose effects we don't quite understand. But ultimately, this set of GAs should.
So I'll just summarize again, just to make sure I understand. You say you know the coupling of all these things because it's perturbation of string theory, and then you wanted to compare it with saying that it comes purely from this geometrical property, the holonomy property, the monodromy in F theory.
Yes.
And that works for some, but not for others. You need to put it.
It works for everything except O7 plus. Okay. So now GA was the 8-dimensional gauge algebra which was living over this curve DA, right? So this formula applied when there were no 7 plus, but now we want to somehow reduce these JAs to the actual 6-dimensional gauge algebra HIs. And each GA will reduce to some HIs weighted by this factor Ni comma A, which tells you whether HI lives over the curve A or not. So over each curve, instead of seeing GA, you are going to see some HIs. Okay, so let's see what naively we can, how we can massage this equation to incorporate this fact.
What caused that breaking, please?
These were the holonomies and the fluxes of NS-NS2 form. So I'm assuming that I don't know how to determine in every situation and every point on moduli space what will be the particular breaking, but let's say some breaking has happened. How does anomaly cancellation happens in that situation? Okay, so now let me just replace, so let me just break GA to this subalgebra. What happens to this coupling? So you're going to again write it as 2 times with some trace Fi squared, where these are the field strengths living in the 6-dimensional gauge algebra as HI.
And now you have this coupling. And the story with the anomaly is that this had better be an integer, so it can be cancelled by an integer number of D3 planes.
Yeah, so I will come to anomaly soon.
Okay.
So these two couplings have to be combined together to figure out the Green-Schwarz contribution to the anomaly. And this will lead to some new conditions. No. And so I'm doing all of these things to figure out the anomaly contribution. Are you asking for the quantization condition?
I was wondering whether, if you got some fraction here, then it looks like you've got fractional D3 brane charge, the flux has nowhere to go. So it looks like a problem.
But it indeed happens. You can have half a D3 brane on NO7 plus.
You can have half an hour. But suppose the total number of, say you had a 6-dimensional compactification of strings, and on that you had a fractional D3 brane charge.
Okay.
This D3 brane charge, should I think of it as 3 brane charge, the same charge of a D3 brane living in the 4-dimensional space? Suppose I've got the 6-dimensional compactification, and then there's the remaining 4-dimensional flat. Should I think of this as the same D3 brane charge that you would have when a single D3 brane lives in this, at a point on this Calabi on this 4-dimensional space?
No, in that case, you will be wrapping, you want to wrap these D3s on these cycles, on these curves. So if you had a compactification to 4 dimensions, the base will be 6-dimensional, and the curves will be 4-dimensional. So you'll be wrapping the whole D3 and you will get a point. You'll get some particles.
But the B is, in my way I was thinking, lived in the 4 flat dimensional space.
No, B, I have not told you how to reduce B. This is just the full B4 in the type 2B, in the 10-dimensional space-time.
But one way of doing it is keeping the B in the 4-dimensional space.
Yes, one way of doing it is that.
And then that is what would couple to D3 branes in the 4-dimensional,
Yes.
extended in the 4-dimensional world volume.
Yes.
Now, in a 4-dimensional space, to have non-zero number of 4-dimensional D3 branes sounds problematic, because the flux has nowhere to go. So if you've got some non-zero charge here, if it was not an integer, you couldn't cancel it by putting real D3 branes. So I was wondering whether that would give you trouble.
No, but there is a delta function, right? this coupling does not contribute at all, because you're not wrapping D3s on the curve.
No, I'm saying you're getting, without the D3 branes, you're getting some charge.
No, so this is a coupling for D3 branes, but there is a delta function.
There's a
It
delta.
happens only when D3 branes wrap this
Well,
curve D.
That was happening at some singular locus on your curve, right?
No, the whole curve is singular. Each curve is a singular locus for the elliptic
Right.
fibration.
So suppose I take that charge and integrate it over 6 dimensions. Over the 6 compact dimensions. That gives me some number multiplying B4.
Compact dimensions are only 4, on 10 dimensions.
Suppose we were doing 6-dimensional compactification.
So if the D3 branes are not wrapping the curve, right?
Let's say there are no D3 branes at the moment.
Okay.
I just have what you have.
Okay.
Then I integrate over the 6-dimensional space. Then I get some number times B4.
Yes.
That number could be either an integer or not an integer. If it was an integer, we could cancel that number by putting a real D3 branes in 4 dimensions. If it was not an integer, you can't cancel it.
Right.
So it looks like you'd have a tadpole that could not be cancelled if you had a non-integer.
Okay.
But a tadpole that could be cancelled if you had an integer. So I was wondering whether there's something special happening if these charges add up to an integer.
Right. So they add up to integer, but except in the case of O7 plus, where you can have a half. Let's see. No, what did I multiply this by? I just changed it by a half, right? Right. So there is a.
So just to understand what this, so this is the D3,
This is integer always.
Always an integer.
Yeah.
Good, then I'm happy.
this is a D3 D7 system, right?
So far, no D3s.
Okay, no D3s, fine.
But whatever, this funny geometry is inducing a D3 brane charge.
Right, so this delta function is indicating the world volume of a D7 brane.
Or some singularity.
Some similarity, and then the R wedge R
Is in everything else. So imagine you were in 6 dimensions.
Right.
There's singularity plus 4 other dimensions.
Yeah.
So then you have an effective D3 brane charge in the 4 non-compact dimensions. And this is like a tadpole for that, which has to be cancelled.
Okay. Right. So we are now looking at the gauge coupling, and I want to reduce my 8-dimensional gauge algebra to some combination of 6-dimensional gauge algebras. So I just naively try to reduce this coupling, which is for GA. Let's write it in terms of HIs. So I will obtain a trace of Fi squared, where Fi is the field strength for the gauge algebra HI. Weighted by NIA, but then there will be an extra factor, let me call it OIA, weighting this. So this will come from the decomposition of GA into the HIs. So this will be some sort of embedding index of HI into GA. So for instance, let's say you want to break SU to SO, some lower SO, then you want to write trace F squared for this in terms of, so these are normalized according to instanton numbers, and the instanton for SO is normalized in terms of there is a half instanton for SO when you view it from the point of SU. Trace. So you need a factor of 2. So this will be the OIA for the SU to SO breaking. So in general, I have some OIAs here, and I'm summing over I's. Okay. Now let's combine all of the couplings over all of these curves. So I just sum over I and A, and I will have an independent field strength for Hi living over all the DAs over which it is shared right now. So right now I have something like, so I have some curve, I have an Hi living here, an independent Hi living here, and an independent Hi living here, where these are some A, B, C. But I know that this should be glued in the 6-dimensional theory. So I want to glue all of them. In effect, I just want to remove the index A on the Fi. So one way to do that will be to, in field theory, how you will do that is you look at each of these stacks, each of these curves. On each of these curves, there is an 8-dimensional gauge theory living there. And these 8-dimensional gauge theories are going in different directions, intersecting at a real codimension 2 locus with each other. So you just simply impose, you can impose the boundary condition that you want, say AI A equal to AI B. This is the gauge connection at the intersection, at the intersection. So this will, once you do that, you just have a single gauge field going over this complicated setup, 8-dimensional, 6-dimensional hybrid setup. And the gauge group will be, because gauge group acts on each point independently, this will be, the gauge group will be identified across this whole 8-dimensional, 6-dimensional hybrid system. So let's say you impose this boundary condition. Then this allows you to remove the A over here. You identify all the field strengths as a single field strength. Okay, and there was a delta function here. So let me just take out this trace Fi squared and collect this, combine this sum with the delta function. So my proposal for the gauge coupling in this situation will be the following, that the gauge coupling takes the following form. The delta function is over some divisor di, and this divisor di is actually a combination of the curves dA. So in the traditional case, we had, instead of index I, we had the index A, and then the delta function was over a curve. The field strength was valued in the 8-dimensional gauge algebra. Now we have the same expression with the index I instead of A. And this is the field strength for the 6-dimensional gauge algebra, and this is some divisor which is some combination of the curves. The combination is determined by the fact whether Hi lives over dA or not, and how Hi embeds inside the 8-dimensional, or how the 6-dimensional gauge algebra embeds in the 8-dimensional gauge algebra.
And in the case without the O whatever, the NIA is by always either 1 or 0. Is this right?
Yes. For NIA was 1 for exactly 1A, and OIAs were 1.
Yeah.
Or they could be, yeah, but they could be broken due to the Tate monodromies, but it was always 1. So people did not notice these factors as well. So let me call this divisor as the gauge divisor for Hi. It's just some name. Okay. So now we combine these gravitational and gauge couplings just as last time. We use the Calabi-Yau condition and do the, right, so let me say something. So if you combine the gauge and gravitational coupling and use the Calabi-Yau condition, you will find that the 6-dimensional coupling will now be integral over the base of B4 summed over where C1b is the cohomology class dual to the canonical divisor on the base. It's dual to K. So this is the 6-dimensional Green-Schwarz counter term.
You had, did you have some, oh wait, there was a term with R4?
No, there was only R squared. Right, so this R squared should also be, sorry, yeah, so. Okay, we want to decompose B4 as some B2s over these divisors
So
A.
in the formula you written down before, wasn't there a 1/24?
Yeah, so that got absorbed into C1b. Delta to dA. So you want to decompose B4 into some tensor multiplets?
So sum over A in the first line is only on the SA term.
Yes, just on this one, and this has a sum over I.
Even the sum is just inside the SA probably. Right?
Yeah.
Should be taken to be just for the second term inside the parentheses.
Yes.
C1b had that sum and that
Yes. Okay. Right. So now we want to square it to get the Green-Schwarz contribution. Square this the coefficient of B4, and then you just dualize it, and you can write the conditions in terms of intersection numbers for divisors on the base. And the conditions are the following.
So here you're putting in that from string theory, you know
Yeah.
exactly what the Green-Schwarz contribution will be in all these.
Yes.
It's not just something that will be cancelled by any Green-Schwarz, but by this particular.
Yes. Okay. So if we compare it to the equations that I wrote in the starting of this talk, we see that the index A has been replaced by I on the left hand side, as it should have, because the algebras are HI. On the right hand side, the DAs have been replaced by the gauge divisors DI everywhere, and K has been replaced by K plus F. So the effective canonical divisor is canonical divisor plus a frozen divisor, the divisor which counts which of these curves are frozen. So SA counted where you have frozen singularities. Right, so with these two modifications, these are the correct anomaly cancellation conditions to use when you have O7+.
But this is the most general.
These are the most general till now. Okay. Right, so let me move on to some applications of these conditions. So let me show you that now with these conditions I can realize some SCFTs which were missing in the previous classification.
Lagrangian SCFTs.
Lagrangian ones, which had a type 2A construction but which could not be constructed in F theory.
Like the first one used.
Yes.
The
So
one
which
with
had
folds. O7. Just putting all the antifolds on the D6 branes intersecting the
Uh-huh.
NS5s. That
Yeah.
would be an example, right? No.
Yeah, but that will be that can be constructed using other compactifications. Okay, so this is, let me describe to you what is the gauge theory. So this is, there are two gauge groups, SUN and SON plus 8. We have a hypermultiplet charge in the bifundamental. So we have a bifundamental, and we have n minus 8 hypers charged under SUN. Let me just write it like this. So this is the theory on the tensor branch. This theory has the property that if you compute its anomaly polynomial, it can be potentially cancelled by a Green-Schwarz term. So this shows in the Lagrangian classification. Now, why can't this be constructed in the usual F theory? So for that, you use the old conditions. So suppose I was using the old conditions here, then I can compute what should be the intersection numbers of my divisors based on a field theory calculation. So it turns out that if you do that, you will find
The old construction is just F equals 0.
F equal to 0, and gauge divisors must be replaced by curves.
Yeah.
So here DIs were NIA, OIA, DA. So you want to set, yeah. Okay, so you will find that so you will assume that SO lives on a single curve, SU lives on a single curve, and the intersection number for the curves should be 2. But I showed to you a few lectures ago that it's not possible if you were to realize SCFT without O7 plus, then there was a result that no two curves can intersect more than once in a consistent F theory setup. Otherwise, you have the problem that you cannot go to the SCFT point at a finite distance in the moduli space of Calabi-Yau.
And let me check if I understand right. Are you saying that you could get this gauge, that you could get these, the anomalies can be cancelled by some Green-Schwarz term?
Yes.
But no, the old F theory construction produces a particular Green-Schwarz term.
Yes,
which does not cancel.
Which you know by a theorem inside that setup that it's not possible.
Cannot cancel this.
Yes. So this is not possible. Right. But now we know one crucial thing, that these need not be the curves. These have to be the gauge divisors, right? So this can come up to a multiple of a curve. So let's see how we can produce this thing. Okay, so for this, let me remind you that this can be constructed in type 2A. And then we will do T-duality to find the type 2B setup, correct type 2B setup to use.
Actually, in about 10-15 minutes, I'm going to have to go, but you should of course continue.
Yeah, I don't have more than 10 to 15 minutes material. Okay. Right, so the type 2A setup which constructs this theory is the following. You have some D6 branes again with some NS5s, and you cut this off with an O8 plane, O8 plus plane. So the O8s live along every direction except the 6th direction. So this was 6 and 9. So the introduction of O8 plus means that the RR charge conservation across NS5 branes is modified, because now you're in massive type 2A theory. And so the correct number of D6 branes jumps by 8 across each of the NS5s. So if you start with n plus 8, you have n here, and then you have n minus 8 here. I claim that this produces this theory. SU group comes from here. The SO group comes from the SU n plus 8 being projected by O8 plus to SO n plus 8. And bifundamental comes from this NS5, and the n minus 8 fundamentals are coming from this NS5. Okay. So Now let's do a T duality of this to type. Let me draw the T dual here. So if you do T duality of this, you find the following configuration. So you have a sphere carrying In from this, a cigar carrying In minus 8, then you have a sphere coming from here, this carries In plus 8, but since you have an orientifold, the orientifolding action is captured by the monodromy of the elliptic fiber. So this is of the non-split type. And the curve carrying O8 plus also becomes an O7 plus after T duality. It's located on a curve which intersects this curve 2 times. And this carries I4 star hat. So this just carries the O7 plus. From there we can assign the gauge algebras SON plus 8 here. So there is some monodromy induced by the on In plus 8 from the intersection of I star 4 with this, and the monodromy is such that SU is projected to SO. And then you have SUN here with bifundamental and fundamentals and minus 8. Okay. So why does this satisfy the new anomaly cancellation conditions? Let's compute. Let's check just this one. We want to really verify this one. This is the main condition. So we want to focus on this one. Right, so we actually want to just verify this, right? And we want to compute what is the gauge divisor for SU and SO. So for SU is just this. So let me label the curves. So this curve is D1, D2, D3 and D4. These are the curves and not the gauge divisors. So gauge divisor for SU is just going to be, it's a trivial Kaluza-Klein reduction. So it's just D3, the curve. And the gauge divisor for SO is coming from a breaking of SUN plus 8 8-dimensional algebra to SON plus 8. And if you remember, this gives us a factor of 2 in this OIA. So we obtain 2 times D2. So now you see D2 and D3 intersect once, so 2 times D2 and D3 intersect twice. So we recover this condition. And we successfully managed to construct the theory. Okay.
So can you construct every Lagrangian theory that satisfies potentially cancelled anomaly equations this way?
Yeah. So yes. So this was one example of that, and there was one more example.
So there were very few theories that you couldn't construct by the traditional.
Yes, and those can be constructed now.
Okay.
And we have not completed the classification because we need to know how the fluxes and holonomy should be incorporated in F theory. So there's some missing physics.
Completed the classification of what? Non-Lagrangian?
Yeah, of all SCFTs when you include O7 plus. That's a very difficult problem because you given a base and I tell you where the O7 pluses are, you don't have an algorithm to compute what are the 6-dimensional gauge algebras. What are the possible 6-dimensional gauge algebras at various points in the moduli space.
I see. So the first lesson was that all the simplest theories that you could write down, namely all the Lagrangian theories that could potentially be consistent,
Yes.
were consistent.
Were consistent, yes. Except
Bit
2.
disappointing, right?
Yeah. No, all the Lagrangian theories which you can write down are consistent up to these some examples which one of them has a field theory explanation. Remember this example I talked about, you have an SU2 and an SO8 with matter in the fundamental time tensor spinner. SO7, sorry, not SO8. This one is in the Lagrangian classification, but this does not exist in F theory, and there is a field theory explanation for why this does not
Just
exist.
remind me, what was the field theory explanation? Very roughly.
So you compactify this down to 5 dimensions, and you look at the Higgs branch. The Higgs branch tells you that
Okay,
the symmetry should be SO8, not SO7.
This is the thing we discussed a bit. I mean,
But I forget now.
yeah, even I forget.
And there is no way to get SO8 from spinor of SO7. I mean, so SO8 has 2 spinors and a fundamental, right? You want fundamental of SO8. But this is spinor of SO8, which is again 8 dimensional, but it comes from spinor of SO8, not fundamental of SO8. So you cannot, yeah. So you wanted to look at the Higgs branch of this theory compactified on a circle or a torus. You will find that the Higgs branch has SO8 symmetry in the fundamental, so you cannot gauge an SO7 inside it with a spinor representation, because this was the flavor symmetry.
Okay, but every theory, I didn't completely understand this, but every theory that you could that appeared from a low energy point of view to be consistent,
Yes, except some handful of cases.
and even those you have some low energy explanation for why they're not consistent.
After non-6 dimensional explanation in lower dimensions.
Okay,
Yeah, it's a low energy argument. Yeah.
Was genuinely consistent. That's the first conclusion.
Yeah.
And the second conclusion is that there are plenty more
Yeah. Non-Lagrangian ones.
theories, and the third conclusion is it's hard to classify all of them.
Yes, if you include O7 plus.
Yes.
Okay. Right. So this might seem to you like not much of a big deal, because I produced such a big machinery in terms of gauge divisors to compute this anomaly. I mean, I was saying that gauge algebras could be shared over multiple curves, but I gave you an example in which gauge algebra lived over every curve. It's just that the gauge divisor was multiplied by a factor of 2.
Yeah.
So I have a more complicated example. I can show you if you have time. It will just take 5 minutes. Okay. So in that example, you have a type 2b dual, and you can compute the spectrum in type 2b, and then you want to match it with F theory.
I have to leave for Skype, which is sorry.
Okay, so we are considering an F theory model on the base P1 times P1. This is the base. Let me say, right, so let me say they have coordinates Z and W, then, right, what do? Right, right, and the discriminant locus is supposed to be each of these P1s individually. Okay, right, what am I doing? Okay, so this is a model where you are wrapping O7 minus with 8 D7s and an O7 plus with 8 D7s, right. So on one of the P1s you have O7 minus with 8 D7s, and on the other P1 you have O7 plus with 8 D7s. You can compute the spectrum perturbatively. This is a compact model. This was presented in the paper of Gimman and Polchinski first. And the gauge algebra that you find, so they consider the case of O7 minus and an O7 minus, but the same techniques generalize to construct the spectrum for O7 minus and an O7 plus. You find that the gauge algebra is SU8 plus 2 USP8s. Then you find that there are hypermultiplets for each pair of gauge algebras. So you have a bifundamental here, a bifundamental here, and a bifundamental here. Then there are two hypermultiplets in the antisymmetric of SU8. So you have two antisymmetrics, and finally you have 1 plus 4 tensor multiplets. So one just corresponds to the coupling to gravity. This corresponds to the canonical divisor in the base. So I'm separating it out. That means that you have 4 tensor multiplets which are exceptional, which are not visible in this P1 times P1. So your F theory setup should have extra 4 P1s. And I should say that these at self intersection 0. So originally your base was a curve with intersection 0 and another P1 with self intersection 0, but now you want to blow up 4 points to produce these extra 4 tensor multiplets. And I propose that you should blow one of them here, this point, and 3 extra points on this. So what happens once you do that? Once you blow up a once you blow up a point here, you produce a new -1 curve, and the self intersections of both of the touching curves decrease by 1. So you obtain -1 and -1 with these 3 points, and when you blow them up, you obtain a configuration like this. And on this you had I star 12, this is the O7 minus plus 8 D7s. On this you had I star 12 hat, this is O7 plus 8 D7s. No, just O7 plus with some number of D7s. In between you obtain some other singularities. There is an algorithm to produce these singularities. This is just the blow up procedure. Okay. Now let me call these divisors, give them some name. Now the question is, where is this? Where are these gauge algebras sitting? This one SU8 and 2 USP8s. They cannot sit in a very trivial fashion, because you see on an I star 12 you should have an SO32 naively. On an I star 12 hat you should have a USP16 naively. On I non split 24 you might have SU12, because there are 2 projections. One projects it to SO, one projects it to USP. Combined projection is SU12, and on these you will expect to have SO8s. Right, so this looks nothing like the spectrum which we have over here. So in order to get the spectrum, for this spectrum to satisfy anomaly cancellation, you can look for various gauge divisors. And it turns out that there is this one unique solution, and the solution is that for SU8, the gauge divisor is 2 times C1 plus D. For USP8 you have so if you use these divisors, you find that anomaly cancels. The anomaly cancellation conditions are satisfied. You can have half whenever you have a USP. USP naturally comes with a half, because you can have a half D3 there. So now let me show you that this makes sense. So let's see why SU8 comes with 2 times C1 plus D. So C1 is over here, we naive 8-dimensional gauge algebra was SO32, and you want to get an SU8 out of it. I'm proposing that you get you just take the 32, you want to get SU8, and I'm proposing that the breaking is such that the 32-dimensional representation of SO32 breaks into 4 times 8-dimensional representation of SU8, and so you will get a factor of 4 times a half. Half is coming from the conversion of SO to SU, so you get a factor of 2 attached to C1. Similarly, you can compute a factor for D. So for D, the 8-dimensional gauge algebra was SU24, and you want to break this to SU8 and a USP81. Right, so I say that the 24-dimensional representation breaks into 2 times 8 plus 8 of this.
Now these are just assertions, or you know that it happens?
These are just assertions.
Okay.
This is a way of justifying that why this thing works. And so you see a factor of 2 for this, and a factor of half because you have a USP.
You're saying it's possible that it happens.
Yeah, yeah. This is the unique, if you take the anomaly cancellation conditions and demand that these are the algebras, you hit upon these.
In this representation, theoretically, you are saying.
Representation theoretically is showing that this is a possibility, but there's some physics for this breaking, right?
Yes, and we don't understand the physics. It's just something which works.
Yeah.
Okay, so yeah, this is the end of my talk.